The binomial series is that 1 plus x or n is equal to 1 plus n times x and plus n into n minus 1 by 2 factorial and so on. So that you know, I am writing only the first two terms, but there is a restriction. The restriction is that x is supposed to be less than 1. For x greater than 1, you cannot write the binomial series. This x should be less than 1. Now if I do apply this on gamma, gamma is equal to 1 over 1 minus v square over c square, and this is equal to 1 minus v square over c square minus 1 over 2. Now I know that v over c is less than 1, so their square will be further less than 1. So it means I can apply the binomial series on this one. And I only go to two terms. The rest of the terms I do ignore, but only two terms I am writing. So approximately this thing is equal to 1 plus half v square over c square. And plus there are other terms, but I am not counting them. I just go up to two terms. And now I can write that, what about P naught? P0 is equal to MC times gamma. And for gamma I can write that this is MC times this value. So this is approximately equal to 1 plus v square over 2c squared. Right? Let's do multiply both sides with c. If I do multiply both sides with c, then P naught c. Okay, keep in mind one thing. P0 is the momentum in the four-dimensional vector, in the four-vector notation, while P1 is the momentum in the three-dimensional, right? It is in the four-dimensional, it is P1, but in the three-dimensional, it is just P, momentum. And if I do multiply C here, so what I will get? I will get mc square 1 plus v square over 2c squared. And there will be definitely other terms. I am ignoring them. And then this is equal. When I write plus this, then approximate symbol is not required. But when I don't write this one, then I will have to write the approximate symbol. And this is equal to do multiply mc square plus this is half c square cancels, and half mv square plus some other terms. Now look to this one. This we already know from our three-dimensional space. This is the kinetic energy, half mv square. This is the kinetic energy. What about this one then? Dimensionally, this one should be energy because energy is aided with energy. So this is also energy. What kind of energy is this one? P0C is also energy because energy is equal to energy. So it means that this is the energy which we call is the rest mass energy. Why? Because look here, mc square, whatever other terms will come, it will include v in it. V will be there. for all other terms except the first term. So if v is equal to 0, if v is equal to 0, then kinetic energy is equal to 0 and all the rest of the terms are equal to 0. But yet in the four-dimensional vector we came to know that there is energy which is independent of momentum. Like this energy, the kinetic energy, is half mv square, or we can write this as p square over 2m. Momentum is 0, kinetic energy is 0. But here the momentum is 0, the momentum, even the velocity is 0, the momentum is 0, and yet we are having some energy with the particle. That's why we call it the rest, and it is the mass energy, mass and the total it's in energy. Rest means v is equal to 0. So that's why we call this one is the rest mass energy. And this is the kinetic energy. This is the energy due to momentum. This is not the energy which is due to momentum. So this thing came into existence by considering the four-dimensional vector. It is not visible in a three-dimensional space. There is no concept in the three-dimensional space. This becomes visible only when you combine the space and time, when you combine the momentum and energy. This is that thing which is coming out, and the mass is coming out to be constant. Because now you see the mass, it is a rest mass because it is not moving. Motion energy is equal to 0. So we call this one is the correction. This is the ordinary energy, and this is a correction to the energy. And this correction to the energy we call is the rest mass energy. And now we come to the P1, and P1 was equal to m times v, right? P1 was equal to, I have written here P prime, okay? So it is v here, mv over, okay, x1. Okay, here I will have to make one correction. This is x and this is t. Now x is equal to vt. Like I can write x is equal to, I have forgotten this t here. X is equal to vt divided by tau. And this is equal to m times v, and then t over tau from here is gamma. So this is mv gamma. P0 was mc gamma. So P1 I can write is mv gamma. And now I can put the values of the gamma here from the binomial series. So mv and then 1 plus v square over 2c square plus other terms. And P1 is equal to mv plus half mv cube over c square and plus other terms. Now we know that this is the momentum which is for the general speed as well, because in all these calculations what we are considering Lorentz transformation. Lorentz transformation is for very, very high speeds. So this one is the ordinary speed momentum, but when the speeds are much greater, very, very fast objects, then this is the correction to the momentum. Their momentum not only remains mv, it is being aided by this momentum as well. So this we call the correction term to the momentum, right? This we call the correction term to the momentum. Like a body is moving, momentum is equal to mv. Now a body is becoming faster. It may remain mv, but when it is very, very fast, like it reaches the speed of light, close to the speed of light, then its momentum will never remain only mv, but there will be some relativistic corrections to that momentum, right? And similarly, the same will be true for this and this. But we, as our motion is only along the x-axis, so we don't go for them because we know about them. These two terms are important in this sense. Now look here, that what about as we studied a proper distance between the two frames, between the two coordinates. Now what about whether they told us that there is a proper length, there is a proper time. Now we will see that whether something is invariant in the momentum and energy as well. And that invariant thing, one comes is mc square. Now see, we already considered from there that it is invariant. So it means this mass is invariant as well, which we call as the rest mass. Rest mass will be invariant in both. And this is the correction term when motion also comes in. Then the energy will change. Energy will be added. The rest mass energy will be added with this term, and so on. So now look for, let's say we are measuring the invariance, and let's say P naught square minus P1 squared. We measure this one. So if you measure this one, then put their values. P naught was mc gamma squared and P1 was mv gamma squared. So this is equal to m square c square minus m square v square, and gamma square you can take as common. So this is equal to, you take m square gamma square as common, then c square minus v square, and if I take the m square gamma square c square as common, then it will be 1 minus v square over c squared. Now think of this one, 1 minus v square over c squared is 1 over gamma square. So this one is cancelling with this one. And P0 squared minus P1 squared is equal to m square c squared. So this is the term which is invariant. This is the invariant term. Invariant term. Now, what does this say to you? Is it giving any new information? M square, C square. Like when we were having MC square, C is invariant, C square is invariant. Here M was invariant, but M square is also invariant. The product of the two is invariant. M square C squared is invariant. And now I can write that what is actually this term. I will have to go for it, that what is this term. Now P naught is what? P naught we have come to know that it is the rest mass energy P naught times C is the rest mass energy it was giving us for V equal to 0. So I can write this one is E over C. P naught C was energy, so P over E over C will be that term squared minus what is P1? P1 is P, the momentum which is in the three-dimensional space, and squared, which is equal to m square c squared. And if I square this one and do multiply with c square, then what it will be? E square minus p square c square is equal to m square c4, because c square is multiplied. And this gives you that energy is squared is equal to p squared c squared plus m squared c4. And it gave you the energy. The energy when there will be some velocity contribution, when there will be some motion, this will be the energy, right? This will be the energy square. When there will be no motion, or when there will be no kinetic, the ordinary kinetic energy, or P will be 0, then you will have only the rest mass energy. So the rest mass energy we got by considering the invariance, by considering the four vector forms in a three-dimensional space. When you consider time is a different entity and space is a different entity, there is no concept of the very famous equation of science, which is mc squared. So there is no concept of it. But when you couple them, when you go for the invariance between them, then you find some extraordinary terms, some correction terms, and some, like we were having no idea of that length can be contracted as well. The two frames will measure different length. The two frames will measure different times. That was the difference between the moving and the rest frame. So, considering them invariant for a proper length and for a proper time, they remained invariant, and as a result, C remained invariant. So, this S over C is tau is proper time. S is the proper length. Similarly, the things will not only stop on C, it will also go for M as well, for the mass. Because the space-time and then momentum and energy. Because we are preparing ourselves for the relativistic mechanics. This is relativistic mechanics. In this relativistic mechanics, in the next lecture, we will cover the products, the different relations in the four-dimensional vector or four vector, like the dot product between two vectors. We know the dot product A dot B is equal to the inner components AX, BX plus AY, BY and AZ, BZ. What will be the dot product under four vectors? Whether it will be the same inner product multiplication or it will be different. And as the dot product is invariant under coordinates rotation, like A dot B is equal to B dot A, whether that dot product will be invariant under Lorentz transformation. So for those we will cover this one. We will also cover some the covariance and the contravariance terms we will cover. We will also cover the relativistic electrodynamics, that what shape the Maxwell equation will get, because now the situation is completely different. It is no speed dependent. Space and time are not separate from one another. In the Maxwell equation, on one side we are having space, while on the other side we are having time. So when we will go to the Maxwell equations, then all the four Maxwell equations can be combined into one equation. And then we will head on toward the general theory of relativity, because for that though these basics will be utilized. Okay, thank you.